Okay, before we get started on 7.4, I want to just do a refresh of graphing log function. With the snow day off, we're several days removed from covering that material, and it's relevant to what we're going to do today. So we won't be doing any graphing today, though. But let's graph f of x is equal to 2 times log base 3 of x minus 1 plus 4. So we want to graph this problem. So we can make a table of values. Remember that whatever value I pick for x, or whatever values I pick for x, we will plug them in to the log right here. And then whatever that number is, when I subtract 1 from it, I'll take the log of it, log base 3 of that number. We want to be strategic because I don't want to do log base 3 of just anything. I want to pick some numbers that are going to work out nicely. Let's off to the side think about some logs that are going to work nicely. I can probably write that a little bit nicer than I did. Let me try that. Oops. Log base 3 of what? What would be one number that would work out nicely? Log base 3 of 1 works nicely. Log base 3 of, what's another one that works nicely? 2 doesn't work nicely. 0 does not actually work at all. 3 does work nicely. What's another one? 9. What's the next one after 9? I'm not going to do all of these on my graph. I'm just asking about numbers that work nice. Log base 3 of 27. What do those numbers all have in common? 27, 9, 3. They're all powers of 3. 27 is a power of 3. It's which power? 3 to the what is 27? 3 to the third. 3 to the what is 9? 3 to the second. It's the second. 9 is the second power of 3. What would the first one be? Log base 3 of 3. It's just 1. It's 3 is the first power of 3. What about the 1 here? 3 to what exponent gives you 1? 0. There's the nice rule. It doesn't matter what our base number is. If we are taking a log of 1, it's always going to equal 0. Now, some other logs that don't work. We cannot have a log of 0. If you're trying to take 3 to some exponent and get a 0, it's never going to work. Can you take a log of a negative number? Can you raise 3 to any exponent and get a negative number? No, that's not possible either. You can only take a log of a positive number. Okay, keep that in mind, and let's come back to this problem. That's not the exact same problem we're dealing with here, but it is related. What would be a nice x value for us to use? 2. Why would 2 be nice? When I plug 2 in, 2 minus 1 is 1, and I get a log base 3 of 1. Right? Right, when I plug 2 in, we get 2 log base 3 of 1 plus 4. We just identified that log base 3 of 1 is equal to 0. So 2 times 0 is 0 plus 4 is 4. Okay, good. What's another x value that would work out nicely? 4 would work out nicely. When we plug 4 in there, we get log base 3 of 3. And then at the end, we have plus 4 still. Okay, So 2 times log base 3 of 3. We just identified that log base 3 of 3 is equal to 1. So it's 2 times 1 is 2 plus 4 gives us 6. Let's do one more just for fun. 6. 6 minus 1 would give us 5. That wouldn't work out very well. 28 minus 1 would give us 27. That would work. Is there a smaller one than 28? 10. If I plug in 10, I get a 9. And log base 3 of 9 we just discovered or just talked about, that's equal to 2. So it's 2 times 2 is 4 plus 4 is 8. Let me give a graphing background so we can graph this one. Four, 6. Okay. Yeah. Is it not supposed to be 8? Let's see. When we plugged in 10, which gave us a 9 there. Log base 3 of 9 is 2. Right? So we have 2 times 2. Because log base 3 of 9, that becomes a 2. So 2 times 2 is 4 plus 4. That's the 8. Is there anything else I should worry about as I connect these? What happens? I think I can see what's happening on the right side. What happens on the left? Does it just start there? Does it keep going? Do we have any asymptote? What kind of asymptote does a log have? Horizontal or vertical? Has a vertical asymptote. And vertical asymptotes have the equation x equals, what number would it be in this case? X equals what? By default, it's 0 unless we have a certain kind of transformation. It would not be 2. 2 actually makes it steeper. It's a 1. We have a vertical line, and the only way a vertical line, if we move a vertical line up 4, that's still a vertical line at the same place. But since the whole thing gets shifted 1 unit to the right, the vertical line gets shifted over 1 unit to the right as well. Our h value was 1. Your rule, in case you've forgotten this, maybe you want to jot it down, but on a log equation, your vertical asymptote is always going to be x equals h, whatever your h is. That's the number inside of the parentheses, but the opposite sign. So now if I come back to the graph, I know I can't touch or cross that, but I get closer and closer and closer. And so there's my graph. Now the point of this, I mean, it's a good refresher. That seems like a long time ago at this point that we did graphing after the long weekend. But the point I'm trying to get to is, let's think about domain and range. What's the domain of that function? This is the piece of it that's really relative to today. What's true about the domain? It involves a 1 greater than 1. The x, but you had to be to the right of 1. 1 is an asymptote, so 1 itself does not work. Anything to the left of 1 doesn't work. X had to be greater than, not even equal to, just greater than 1. What about the range? All real numbers. It goes up forever and down forever. So negative infinity to positive infinity, or all real numbers would be your range. That domain piece is what I want you to remember as we move into today's section. I want you to remember that the domain of a log is not all real numbers. There are restrictions on what you can take the log of. Keep that in mind as we transition now into section 7.4. I'm going to get rid of the graphing background. So we will do no graphing today. So 7.4 is titled Solving Logarithmic Equations and Inequalities. Okay, so I want to start off with this because this is a type of problem that we already did. We've already done this type of problem. This what we really last unit, we would have just said evaluate. There probably wouldn't have been equals x. It would have just said log base 64 of 4, and we have to figure out what that equals. There is a question in today's section like this, even though it's not really new material. But I want to make sure to differentiate between this and the new material. So, how can we do this problem? It's really saying 4 is a power of 64. What power is it? Well, since 4 is actually smaller than 64, might seem easier to think about it the other way around for a moment. What can you do? What would you do to 4 to get to 64? 4 to what power is 64? 4 to the third power is 64. But this is the other way around. This is 4 is a power of 64. So it'd be 1/3. You would do the third root of 64 to get 4. So what's x? 1/3. If you weren't sure of that, you could have also rewrote that in the other form. You could have rewritten it as an exponential problem, in which case it would be 64 to the power of x is equal to 4. Then you can write both as powers of the same number. So hopefully you would recognize that 64 is a power of 4. So that's 4 to the 3x is equal to 4, and that's really 4 to the first power. Same base numbers, so now you could just focus in on the exponents. 3x has to equal 1, divide by 3, and you got your answer of 1/3. Okay, that's what we did in the last section. And you will see a problem like that make a resurgence here. And since the x was not in the log, I'm not worried about a domain problem here. Okay, we didn't have to worry about that in the last section, but that's not what most of today's problems will look like. Instead of having x apart or away from the log, oftentimes we're going to have x in the log itself. For example, we might have log base 8 of x is equal to 4/3. And we have to figure out what the x value is. Notice the x is in the log. We can't take a log of just anything. So we will have to check our answer and make sure it works, kind of think about the domain piece of it. Wouldn't it be nice, isn't it our goal to just get the x by itself, isolate the x? Wouldn't it be nice to get rid of a log? Sure. So we need to think about inverse operations. So if we have a log, what was log the inverse of? Do you remember that? We introduced it last week. We started off dealing with exponential equations, and we said that the log was the inverse of exponential. So then, therefore, The inverse of log is exponential. So I'm going to use an exponential equation here, or I'm going to exponentiate this equation. So when I say exponentiate, I don't mean put an exponent on it. I mean make those two things exponents on the same base number. Very important that they're on the same base number. What base number should I choose to use? If I'm trying to get rid of a log base 8, I would like to use a base of 8. So what I will do is I'm going to make a new equation, kind of working backwards from what we did last week. Last week, if I had the same base numbers, I just looked at the exponents. Now I'm making them exponents again, basically. The left side is going to be an exponent on 8, and the right side is going to be an exponent on 8. You can do that. You can exponentiate them, make them both exponents, as long as you use the same base number on both sides. So all I did was I put an 8 under both of those. What happens when I take log 8 to the log base 8 of x? Those are going to cancel each other out. They're inverse operations. X is no longer in a log or in an exponent. It's just by itself. On the right side, I have 8 to the 4/3. We did problems like that in chapter 6. That was first semester. That was before finals. That's a while ago. Does anybody remember, anybody know off the top of their heads without using a calculator what 8 to the 4/3 is? Anybody remember? The denominator is a root. So it's a third root of 8, and then it's to the 4th power. What is the third root of the cube root of 8? 2. So it's 2 to the 4th power, which is 16. Third root of 8 is 2 to the 4th power, gives us 16. 16 was the answer to that problem. Now, I got a little bit ahead of myself because I already boxed in my answer, assuming it was correct. When in reality, there's not necessarily, I got to be careful because I can't take the log of just anything. If I plugged this into the problem, it would read log base 8 of 16. Is it okay to take a log of 16? Yes. What can you not take the log of? 0 or a negative number. We don't have that scenario here. It's okay. Our answer is fine. But sometimes we will have an issue. Okay, let's try another problem. Log base 16 of x is equal to 5/2. I want to get rid of a log, so I will exponentiate. What base number will I use this time? If you want to get rid of a log base 16, you need to use a base of 16. So 16 to the left side is equal to 16 to the right side. Notice the left side became an exponent. The right side became an exponent. Both on the same number, same base number. Now 16 log base 16 cancels on the left side, leaving you with x. On the right side, I have 16 to the 5/2. The denominator is 2, so it's a second root, also known as a square root of 16 to the 5th power. Square root of 16 is 4. 4 to the 5th power. 1024. 1024. Is it okay? When I plug that in, does that work? I would have log base 16 of 1024. Is that okay? Yes, it is. Sometimes we'll have equations that have a variable on both sides of the problem. Sorry, I meant to say a log on both sides, not just a variable, but a log on both sides. Log base 4 of x squared is equal to log base 4 of negative 6x minus 8. Here I have a log on both sides. Wouldn't it be nice to get rid of the log? How can we get rid of a log? By exponentiating. It's like one of my favorite words, exponentiate. So what base number? 4, and isn't that going to get rid of both logs at the same time? That's good. We actually like it when there's logs on both sides. It makes it usually easier. Except because it's easier, they might be a little bit nasty with the type of problem they give you. Like in this case, I get a quadratic. So both logs went away. I get x squared is equal to negative 6x minus 8. I would recommend setting that equal to 0. Hopefully we can factor it. If not, we can use completing the square or quadratic formula. Move everything over to one side, x squared plus 6x plus 8 is equal to 0. This one is factorable. X plus 4 and x plus 2. So if I solve the first one, x plus 4 equals 0, I get an answer of negative 4. And the second one, x plus 2 is equal to 0, I get an answer of negative 2. So I got two answers. We need to check them and make sure they actually work. You have to check both of them. It is possible that they will both work. It's possible that one works and one doesn't. It's also possible that neither of them work. So we need to check them and verify. So if you plug, let's start with negative 4. If you plug in negative 4 to the left side, I would have log base 4 of 16. Is that a problem? That doesn't appear to be a problem. Plug it into the right side. Log base 4 of, it's a negative 6 times negative 4, positive 24, minus 8. Oh, log base 4 of 16 equals log base 4 of 16. They're both the same thing, and they're both positive, so it's perfectly fine. Now let's plug in negative 2 and see if it works. So plug in negative 2 squared, we get 4. Plug it in on the right side. Negative 6 times negative 2 is positive 12. Minus 8 gives us 4 also. Oh, they're both the same thing, and they're positive, so both of those answers work. There are two answers to that problem. Let's do another one. Log base 3 of x squared minus 15 equals log base 3 of 2x. Good news is, logs on both sides, they're both the same kind. I'm going to exponentiate. Now I'm starting to get lazy. Instead of rewriting it, maybe I can just do that. Is that okay? I made them both exponents on 3. By just writing in the 3, I think that's okay. So now I have x squared minus 15 is equal to 2x. I want to set it equal to 0. I want to slide the negative 2x in there before I get to the 15. looking for two numbers that multiply to negative 15, that add to negative 2, 3 and negative 5. So if x plus 3 equals 0, we get an answer of negative 3. If x minus 5 equals 0, we get an answer of positive 5. But let's check. There's a good chance, and since I'm doing another example, they're not both going to work. Let's plug them in and verify. Let's plug in negative 3 first. Negative 3 squared is 9. 9 minus 15. Want. Do I really even need to go any further? I will, but I already know that's a problem. Plug it on the right side. 2 times negative 3, negative 6. But don't they both say the same thing? But they're both undefined. You can't take a log of a negative number. I don't care that it says the same thing on both sides. Neither of them are okay. So negative 3 does not work. Let's check 5 to see if it works. Sometimes neither of them work. 5 squared is 25. 25 minus 15 is 10. Plug it on the right side. 2 times 5, also 10. It's positive. Both of them work. That one is A-okay. So only one answer to that problem. Remember, it is possible for there to be 1, 2, or 0 answers on those. Sometimes neither of them work. So that was the equation piece. If you remember the title of this section, solving logarithmic equations and inequalities. I'm not going to spend a lot of time on inequalities, but we do need to do a couple. Log base 2 of x is less than 4. Once again, I'd like to get rid of the log. How can I do that? By exponentiating. I would exponentiate with a base of 2. So on the left side, we're left with x. On the right side, I have 2 to the 4th power. Nothing canceled out. Go ahead and do the math. 2 to the 4th is 16. Seems easy enough, but because it's an inequality, there's an infinite number of answers. We're just saying everything less than 16. Is that actually correct? Does every number less than 16 work when you plug it in? Yeah, some numbers work, but not all of them. So on an inequality, we really need to focus in on the domain. You can't possibly plug in every single number, not like you can on the equations. So let's consider the domain. And to consider the domain, look at what you're taking the log of. In this case, it's pretty simple. We're taking the log of x. What do I know about that x? Since I'm taking the log of it, it must be, it's going to be the same thing on every one of these. It has to be greater than 0. You cannot take a log of 0, and you cannot take a log of a negative number, only positive numbers. Solve that if necessary. This one's already solved, so I know x has to be greater than 0. Are those two things contradictory? Less than 16, greater than 0? Somewhat. Some of the numbers less than 16 are not greater than 0. Would you agree? So only the ones that are greater than 0 work. So it has to be between 0 and 16. Both of those are open intervals. 16 itself did not work. 0 itself does not work. Has to be less than 16, also has to be greater than 0. Sometimes it's not contradictory at all. If I would have changed that to a greater than sign, you would have just had x is greater than 16. There would have been no restrictions. You could have just left it as x is greater than 16. No problems at all. But sometimes there is a restriction. That's what I wanted to look at. Yeah, so the question is it possible that I give you an equation or inequality where there's logs on both sides, but they have different base numbers? In this class, no, that will not happen. If there's logs on both sides, you'll be able to eliminate both of them at the same time. So I have to exponentiate. It's a 5 this time. Two x plus 1 must be less than or equal to x plus 4. Subtract x from both sides. Subtract 1 from both sides. X is less than or equal to 3. Are all of those numbers going to work? Chances are that they're not. Let's check the domain. However, we have two domains here going on, don't we? We really need to check both of them. I have two things to check on my domain here. I know that 2x plus 1 must be greater than 0 since I'm taking the log of it. And I also know that x plus 4 has to be greater than 0 since I'm taking the log of them. In both cases, it's what I'm taking the log of. Go ahead and solve both of those. I have two pieces to that domain. I can actually combine those together into one domain. A number line might help me understand that better. I need -4 and -1/2 in the same number line. -4 is the smaller one, so it's further to the left. -1/2 is further to the right. Go ahead and graph both of those on the number line, the same one. Greater than -1/2, so to the right of -1/2. Greater than -4, so to the right of -4. Don't both of those have to work? If both of those have to work, they don't both work until I get to the right of -1/2. Starting here is where both of them worked. If it was less than -1/2, then one of the logs is going to be problematic. So I can summarize the domain as x has to be greater than -1/2 because they both have to work. It's the one that's more restrictive. Okay, so now compare that with our answer set. We said that x has to be less than or equal to 3. Is every number less than or equal to 3 going to fit in our domain? Not all of them, right? Once we get to -1/2, we have a problem. So -1/2 is less than x is less than or equal to 3. The domain piece is always going to be an open interval. Always have greater than there, not equal to. Number 7, the problem had an equal to, so that's why I have an equal to with the 3, but never with the -1/2 piece, never with the domain piece. Once again, sometimes your answer set is perfectly fine and all of it is within the domain, and then you don't have to restrict it. I'm giving you the examples where it's a little bit more work because you do have to restrict it. All right, and that is the extent of the notes. Your assignment, let me put your assignment up here. I think I have it handy. Right here. Sorry, my computer's being a little slow. But that 7.4 assignment there, page 480. There we go. You're right on it. There we go. That's the assignment we're looking for.